Welcome to the 8th lecture on the category of vector spaces titled Basis. Let's begin with a review of the concept of linear independence. A subset A of a vector space is linearly independent when for all finite subset v1 etc. vn of A, and for any scalar t1 etc. tn, if t1 v1 plus t2 v2 plus etc. plus tn vn is equal to 0, then t1 equals t2 equals etc. equals tn equals 0. In particular, if the set v1 etc. vn is linearly independent, then there is a unique way to write a vector in the span of v1 to vn as linear combinations of those vector v1 to vn. We also record that if you're a subset of a linearly independent set, you are linearly independent as well. We proved a few important results about linear independence. For instance, we showed that if A is a subset of a vector space, and omega is in the linear span of A but not in A, then the union of A with a singleton omega is linearly dependent. We also showed that if A is linearly independent, and yet the union of A with a singleton omega is linearly dependent, then omega is in the linear span of A. Let's start with a generalization of a theorem from the previous lecture. Let's fix a subset A of a vector space. I'm going to introduce a new vector space, which consists of those functions from A to the scalar field k, which take non-zero values only finitely many times. I will call these functions finitely supported functions from A to k, and I write k to the superscript A to the subscript finite for the vector space of all those functions. You can check that indeed this set is a subspace of the space of all functions from A to k. Now let f be a finitely supported function from A to k. And let's write its support, that is a pre-image of the scalar field without zero, that is the set of vectors where the function takes non-zero values, as v1 etc. vn. Then I define sigma f as a sum from j equals 1 to n of f evaluated as v sub j times v sub j. So you take the support and you make a linear combination of the vectors in the support using, for coefficients, the value of the function at those vectors. So in particular, it's easy to check that we have defined a linear map called sigma from the space of finitely supported functions from A to k to the vector space in which A lives. I would like to know when is this function surjective and injective. Sigma is actually surjective if and only if the linear span of A is actually the entire vector space, whereas sigma is injective if and only if A is linearly independent. So let's prove this theorem. First, surjectivity is reasonably obvious because it's very easy to check that the range of sigma is in fact the linear span of A. I'm going to do it to show you how to use these notations a little bit. So let V be a vector in the linear span of A. Therefore, V is a linear combination of elements in A. So V equals T1 V1 plus etc. plus Tn Vn for T1, T2, etc. Tn scalars and V1, V2, etc. Vn elements in A. So now I'm going to define a finitely supported function from A to k. If omega is in A, I define f of omega as t sub j if omega equals v sub j. And if omega is none of those vectors, then I simply set f of omega to be 0. So you see that f is finitely supported since the support of f is a subset of the finite set v1 etc. vn. So I can apply sigma to this function f. And by definition, this is equal to the sum from j equals 1 to n of t sub j v sub j, which of course is a vector v. Thus, for any v in the linear span of A, I found an element of this vector space of finitely supported functions from A to k, so that sigma of that function is indeed v. So the range of sigma is indeed a subset of the linear span of A. But then if you look at the definition of sigma, you'll notice that sigma is indeed valued among linear combinations of vector of A by construction. So that gives us our dual inclusion here, and we can conclude that the range of sigma is indeed the linear span of A. Now let's look at injectivity. So first I'm going to assume that A is linearly independent. I'm going to take f, an element of the kernel of sigma. So f is a finitely supported function from A to the scalar field k, such that sigma of f is 0. Let's assume that f itself is not the zero function. And again, let's take the support of f, that is a pre-image of the scalar field without 0, that is a set of those vectors where f does not take the value 0, and let's write it as v1, etc., vn. It's a finite set by assumption on f. So by definition, what is sigma of f? Well, it's 0 because f is in the kernel of sigma. But it's also the linear combination, sum from j equals 1 to n, of f at v sub j times v sub j. And since A is assumed to be linearly independent, we can conclude that all the coefficients f of v sub j must be 0. Well, that's a contradiction because we exactly chose the vectors v1, v2, etc., vn as those vectors where f does not take the value 0. Therefore, the only thing we have left is that f must have been 0 to begin with. So what does that tell me? It tells me any function in the kernel of sigma must be 0, and of course 0 is in the kernel of sigma. Therefore, the kernel of sigma is reduced to a singleton 0, and sigma is therefore injective. Now, let's prove the converse. Assume now that sigma is injective. Let's take some arbitrary finite subset of A. Let's call it v1, etc., vn. And let's suppose we found scalars t1, etc., tn, such that t1 v1 plus etc. plus tn vn is equal to 0. I'd like to prove, of course, that all those coefficients, t1, t2, etc., are all 0, so that I can conclude A is linearly independent. So how am I going to do that? Well, I'm going to play a bit the same game I played in the previous slide. So you're going to define f as a function from A to the scalar field k. To a vector in A, it associates the value t sub j if that vector actually equals v sub j, and the value 0 otherwise. So it's exactly the same thing we saw when we did the surjectivity proof. And again, we can calculate sigma of that function, which is a finitely supported function from A to the scalar field, and we get that it is the linear combination t1 v1 plus t2 v2, etc., plus tn vn. And that by assumption is 0. So it means that sigma of that function is 0, so that function is in the kernel of sigma. But the kernel of sigma is reduced to a singleton 0 since I assume that my linear map sigma is injective. So t1, etc. equal tn must all be 0. That's reading from the fact of what the function f is. All the values the function take must be 0. Therefore, we have indeed shown that A is linearly independent. So let's make a couple of observations. First, if A is finite, the theorem is in fact a theorem from lecture 7. The notations there were easier because when A is finite, the space of finitely supported functions from A to the scalar field is just the space of all functions from A to the scalar field. And in fact, we can even dispense altogether with this notion. It's very easy to define sigma because it only involves finite sums by construction. The problem here is that when A is possibly infinite, I can't simply write an infinite sum of vectors because I don't know what that means. That would require some sort of analysis background, some sort of norm or topology or something to make sense of limits that I know what an infinite sum is. We are not dealing with this here. We're dealing with purely algebraic situation. So I can only add finitely many terms. So this is why we have to have this more complicated setup. The second observation is that what's interesting, of course, to us is when is sigma an actual linear isomorphism? Well, it's a linear isomorphism between the set of finitely supported functions from the subset A to the scalar field k, exactly when those two conditions are met, which is that the linear span of A is everything, so A is a spanning set, and A is linearly independent. And when those two conditions are met, and exactly when those two conditions are met, this mat sigma becomes an isomorphism. So with that in mind, we can now define the notion of a basis. A basis of a vector space is a subset of that vector space which spans the entire vector space, yet at the same time is linearly independent. This is, of course, a very important notion in this course and in linear algebra in general. So as we just observed in the previous slide, if we have a subset B of a vector space, that subset B is a basis if and only if the map sigma we defined in the previous slide is a linear isomorphism. So let's look at a few examples, and I'm going to focus on finite basis, even though the definition allows infinite basis just fine, but the finite ones are going to be the more important ones in this course. So first, let's fix a natural number n, and remember that our scalar field k raised to the power n is in fact a vector space. And for that vector space, there is always a very simple basis called the canonical basis, which consists of those vectors e1, e2, etc., en, which are 0 at all coordinates except one of them, where you put the value 1. Remember that 0 and 1 are the two elements we are sure exist in a field. So why is this a basis? Well, it follows fairly easily from a simple calculation. If you have x1, etc., xn element of your scalar field, then the n tuple x1 to xn is equal to the sum x1 times e1 plus x2 times e2 plus etc. plus xn times en. It's an immediate calculation. But then, once you make this observation, two things become obvious. First of all, the span of e1, e2, etc. en is obviously k to the n. We just actually proved that. On the other hand, suppose that I set this linear combination here with the x1, e1, etc. plus xn en to be 0, to be the null vector. Then it's just a matter of reading that it tells you immediately that x1 equals x2, etc. equals xn equals 0. So this family is also linearly independent. So it's a basis. So now I'm going to give you a little exercise. So we're going to work in the vector space of polynomials with real coefficients and of degree at most 3. I call that R sub 3 of x. And I'm going to give you 4 polynomials, but not explicitly, though if you think about it for a moment, almost explicitly, called P0, P1, P2, and P3. And they have the following property. P0 is 1 at 0, and it's 0 at 1, 2, and 3. P1 is 1 at 1, and it is 0 at 0, 2, and 3. P2, again, same principle, is going to be 1 at 2, but it is 0 at 0, 1, and 3. And you can guess for P3 what happens. And I want you to show that this set of these 4 polynomials, P0, P1, P2, P3, is a basis for my vector space of polynomials with degree at most 3. I suggest you pause, and I'll give the solution on the next slide. So let's solve this problem. How do we prove a set is a basis? We prove that that set is linearly independent and it spans the entire vector space. So let's start by showing that the set P0, P1, P2, P3 is in fact linearly independent. By definition of linear independence, let's start with 4 scalars T0, T1, T2, and T3 such that T0 times P0 plus T1 times P1 plus T2 times P2 plus T3 times P3 is equal to the 0 polynomial. I want to prove that all these scalars, T0, T1, T2, and T3 are 0. But consider this expression here, this linear combination of the polynomials. It's itself a polynomial, so I can evaluate it at various values. And let's evaluate it at 0. So I know that P0 of 0 is 1, but P1, P2, and P3 evaluated at 0 are 0. That is the hypothesis on my polynomials. So if you think about it, T0, P0 plus T1, P1 plus T2, P2 plus T3, P3 evaluated at 0. On the one hand, it's 0 because, well, that linear combination of polynomials equals 0 no matter what. But on the other hand, it's equal to T0 times P0 at 0, which is just T0, because everything else vanished. So we have shown that T0 equals 0. And you repeat that same argument, but instead of plugging 0, you plug 1, 2, and 3, and each time you will get that T1, T2, and then T3 are all 0. So indeed, our family of polynomials here is linearly independent. Then we also need to prove that it spans the entire vector space. So let Q be some polynomial of degree less or equals than 3. I want to prove that Q is a linear combination of P0, P1, P2, and P3. So what I'm going to do here is I'm going to compute the following polynomials. It's Q minus Q at 0 times P0 minus Q at 1 times P1 minus q at 2 times p2 minus q at 3 times p3. So now let's calculate this polynomial at 0. So we get q0 minus this linear combination here with the various polynomial p0, p1, p2, p3 at 0. But you know that p1, p2, and p3 are 0 at 0. So what you're left with is q minus q0 times p0 at 0, which is 1. So q0 minus q0 gets 0. Similarly, let's calculate this polynomial at 1. Well, again, we're going to get 0 for the same reason. You get q of 1 minus, and all what's left in this sum here is q1 at p1 of 1, which is 1. Everything else is 0. So again, we get q of 1 minus q of 1, and we get 0. Same at 2, same at 3. So this polynomial has 4 distinct roots, yet it is of degree at most 3. We can conclude that, in fact, this polynomial must be 0. What does that mean for this polynomial to be 0? It means q is equal to the sum from j equals 0 to 3 of q at j times p sub j, just by solving. So indeed, we've seen that every polynomial of degree at most 3 is a linear combination of your set p0, p1, p2, and p3. Therefore, this set is a basis of the vector space of polynomials of degree at most 3. So what are bases used for? They have two fundamental uses. One is to help define the notion of dimension, and that's the subject of the next lecture. And the other one is to help us construct linear maps. So if B is a basis of a vector space V, if W is a vector space, and if little omega is a function from the basis B to the space W, then there exists a unique linear function phi from V to W, such that for any x in the basis B, phi of x equals omega at x. So what we're saying here is that if you give me a function which goes from a basis to some other vector space, then there is actually a linear extension of that function to the entire space, and it is in fact unique. So let's first prove that this function actually exists. So I'm going to refer to this linear isomorphism at the beginning of the lecture, which we called sigma, which, as you recall, two finitely supported functions from the basis B to the field K associate this linear combination here, sum of f of V times V, where V ranges over all possible vectors in the support of F. And I'm going to also introduce a new function. So again, if F is a finitely supported function from B to the scalar field K, and if, for simplicity, I write it support V1, etc., Vn, that is a set of vectors where F is not 0, then first note that this is a subset of the basis B, and second, as such, it makes sense to define psi of F as a sum from j equals 1 to n of F at Vj, that's a scalar, times omega at Vj, that's a vector in W. So we use the function f to give us a coefficient on how to combine the vectors in W that are given as images of vectors of the basis B. Alright, so this psi map is easily checked to be linear. It's very easy just looking at the definition. And then what I claim is that phi is the map phi of the theorem can be computed as psi composed with the inverse of sigma. So the inverse of sigma takes a vector in V, transforms it into some sort of finitely supported function from B to K, and then to that function you apply psi, which gives you this linear combination of vectors in W. And I claim that this is it. This is a linear map. Well, it is a composition of two linear maps, so certainly that is the case. And if I take an element in my basis, let's say x, then phi of x is indeed equal to omega at x. To see that, let's do the calculation really quickly. Take x in the basis. What is sigma inverse of x? So we're looking for a function f such that when you use that function as coefficients, in a linear combination of vectors of B, you're going to get x. But x is already in B, so there's an easy way to write x as a linear combination of vectors in B, namely 1 times x. So that means that I could take for function f the function that's 1 at x and 0 everywhere else, and that works. Sigma of that f is x. So in other words, sigma inverse of x is that function that is 1 at x and 0 everywhere else. Then you plug it into psi. What happens? Well, it's 0 everywhere except at one value, namely x, And so we get f of x times omega at x, but f of x by definition was 1, so you just get omega at x. So phi at x is indeed given by omega at x. Uniqueness follows from the linearity and from the fact that indeed B is a basis. So let's say you have a map, let's call it phi again, whatever, which is linear and has a property, and when restricted to B, it is equal to omega. And let's pick V an arbitrary vector in the domain of that map. So you can write V as a linear combination of vectors in your basis because the basis is spanning, and that linear combination is unique because the basis is linearly independent. So V equals T1 V1 plus etc plus Tn Vn in a unique way, with V1 etc V1 subset of the basis B and T1 etc Tn scalars. But then, since our function is linear here, and since we know what it does to vectors in B, by definition we use this map omega there, we can calculate the image of V by our map is T1 omega of V1 plus T2 omega of V2 plus etc plus Tn omega of Vn. It has no choice. So any function that is linear and restrict to omega on the basis B must assign to a vector, arbitrary vector V of your vector space, this particular value right here. So the map is unique, and we showed it exists. So indeed, bases allow you to construct linear maps by simply giving values to elements of a chosen basis. So in order to discuss the fundamental problem of whether bases actually exist at all, I'm going to characterize bases as maximal linearly independent sets and minimal spanning sets. Remember that the power set of a vector space, or any set, is ordered by inclusion. So it makes sense to talk about maximal elements and minimal elements in the sense of inclusion here. So we fix a vector space V, and we take two subsets of that V. One is called S, and it has a property that the linear span of S is all of V, and one is called L, and L is a subset of S, of the spanning set, and L is linearly independent. And then I'm going to define a collection of sets. So script L here is actually a subset of the power set of V. It's a collection of subsets of V. And they have several properties. First of all, to be in my script L is equivalent to A being a subset of the spanning set S, B to contain the set L, and C to be linearly independent. So those are the three properties that characterize the element of script L. Then I claim that if you take any element B in script L, the following assertions are equivalent. B is maximal in script L for inclusion, and B is a basis for V. So bases are found among the maximal elements in such sets. B maximal in script L here for inclusion means that if there is any other set which is in script L and contain B, then in fact they must be equal. So let's proceed with this equivalence. First, assume that you're given a maximal element called B of script L. And let's show that this B must be a basis. The core result that's going to help me prove this, which I reminded you of in the introduction, is that if you give me any linearly independent set A, and somehow A union a singleton W becomes linearly dependent, then W is in fact in the linear span of A. So let's prove this result. So first, I want to prove that if B is maximal in L, then B is indeed a basis. To that end, I'm going to remind you of a result I also included in the introduction of this lecture. If A is a linearly independent subset of our vector space, and A union a singleton omega with omega a vector in your vector space is linearly dependent, then omega is actually in the linear span of A. If B is an element of the script L, then B is linearly independent. If I pick in particular a vector in the spanning set S, we'll call it V, and V is not in the span of B, so B doesn't span everything, then I know that B union the singleton V must be linearly independent by this result that I just quoted. But then it means that B union the singleton V must be in script L. But then that means that B is not maximal because you found a set that contains B and yet is not equal to B in that collection script L. Therefore, if B is maximal, then we've just shown that the span of B must contain the entire set S. But we know a lot of things about span, so we know that the entire vector space is equal to the linear span of S. That's the assumption on S. But since S is a subset of the linear span of B, then we can conclude that the linear span of S is a subset of the linear span of B. And of course, the linear span of anything is just a linear span. So we've shown that the entire vector space is a subset of the linear span of B. Of course, the linear span of B is a subset of the whole vector space, so double inclusion tells us that the linear span of B must be the whole of the vector space. So if you are linearly independent and maximal, then you must span the whole space as well. As a linearly independent spanning set, you're a basis. Now, let's prove the converse. So I have a basis inside the script L. Some element in script L is actually a basis. I want to prove that it must be maximal. So again, I'm going to use one of the results I recalled in the introduction. If you have a subset A of a vector space, and you have a vector omega that's in the linear span of A but not in A, then A union the singleton omega must be linearly dependent. So let B be an element of script L, which is also a basis for the entire vector space. I want to prove that B is maximal in L, so I give myself C, an element of L, which contains B, and I want to prove that B equals C. So let V be an element in C. Note that since B is a basis, V is in the linear span of B. And note also that since both B is a subset of C and V is an element of C, B union a singleton V is a subset of C. But C is linearly independent since it is chosen as an element of script L. So B union the singleton V is linearly independent. And from that and the result I just recalled, we must conclude that V is an element of B. Indeed, if V is in the linear span of B but not in B, then we knew that B union the singleton with V would be linearly dependent, and we just saw that is not the case here. So since any element V of the set C is actually an element of the set B, we have concluded C is a subset of B, and therefore we have that C equals B. This indeed states that B is maximal. Anything that contains B in L must be equal to B if B is a basis. So this concludes our theorem. So now we get an important corollary of our theorem. A subset B of a vector space is a basis for that vector space if and only if it is maximal among all linearly independent subsets of your vector space. And the proof is immediate. It follows from our theorem by setting the spanning set S to be the entire vector space and the linearly independent set L to be the empty set. Then the conclusion of our theorem is exactly a corollary. So we're now going to prove a sort of dual result to the previous result about maximal linearly independent subset being basis. Namely, now we are going to discuss minimal spanning sets. And that is interesting because when we discuss linear spans, we had this question, which was, oh, okay, so a subspace is a linear span of many of its subsets, but in general, it would be natural to try to look for a sort of minimal subset that span the whole subspace. And under what condition can we do that? Well, the theorem that I'm going to prove now is going to tell us exactly that those minimal spanning sets will have to be bases. So let V be a vector space. The setup is a bit similar to the one we had before. We pick two subsets of V, S and L, with S spanning all of V and L linearly independent. And we also assume that L is a subset of S. And then we look at the sets in between L and S, but which span the entire vector space. And we call that script S. So script S, again, is a collection of all subsets of S, which contain L and span the entire space. And now I'm going to prove that for any element B in that script S, the following assertions are equivalent. B is minimal in S for the inclusion, and B is a basis for the vector space. So let's prove our result. let B be an element of script S. I want to show that if B is linearly dependent, then B is not minimal. What does that mean for B to be linearly dependent? It means that there exists a finite subset v1 etc. vn of B, and scalars t1 etc. tn not all 0, such that t1 v1 plus t2 v2 plus etc. plus tn vn is in fact 0. So now let I be the set of k between 1 and n, so that v sub k is not an element of L, the linearly independent set of the theorem. Since L is linearly independent, I can conclude this set I is not empty, because otherwise it would mean that v1 etc. vn would all be in L, and since L is linearly independent, there is no way to write 0 as a linear combination of v1 etc. vn with not all coefficients being 0. For the same reason, in fact, there must be a k element of this I, so that t sub k is not 0, because if for every k in I, t sub k is 0, then your linear combination t1 v1 plus etc. plus tn vn is really a linear combination, again, of vectors in L. Those that are not in L have 0 in front of them as a coefficient, and so they don't really contribute. And again, by linear independence, that linear combination cannot be 0 unless all the coefficients are 0, which we assumed here is not the case. So what I can do now is I can take this vector v sub k and express it as a linear combinations of the other vectors v1, v2, etc. vn, but without v sub k. Since t1 v1 plus t2 v2 etc. plus tn vn equals 0, you take the tk vk term, put it on the other side of the equation, and multiply the whole equation by minus 1 over t sub k, which is legitimate since t sub k is not 0 by our choice, and you get this expression here. Now why this is useful is because it shows to you that v sub k is an element of the linear span of B without v sub k. Now of course, if you're a vector in B but you're not v sub k, you are, well, in B without v sub k, so you're in the linear span of B without v sub k. So all of B is in the linear span of B without v sub k. Now B was chosen in script S, therefore B spanned the entire vector space. But since B is a subset of the linear span of B without v sub k, then the span of B, that is the entire vector space, is a subset of the span of B without v sub k. And since the other inclusion is trivial, you concluded that the span of B without v sub k is the entire space. Moreover, we made sure that k was an element in this set I, that is v sub k is not in L. Since L is a subset of B, when you remove v sub k from B, L is still in there. And it's trivial to know that B without v sub k is, of course, a subset of the spanning set S. So B without v sub k has all the properties needed to be an element of script S. But of course it's contained in B but not equal to B, so B is not minimal. So what we've shown, to summarize, is that if B is in script S and is linearly dependent, then B is not minimal, so by contraposition. If B is minimal in script S, then B is linearly independent. And we already know, because everything in script S is like that the span of B must be all of V. So that means that B is in fact a basis as a linearly independent spanning set. So it shows that minimal sets in S are indeed bases. Now let's prove the converse. So you have a basis in that script S. And I'm going to take C, another element of script S, but which is contained in B. And I want to show that C equals B. Now, since B is a basis, it's linearly independent. So any subset of B is also linearly independent. So C is linearly independent. But if C is assumed to be an element of script S, then it also spans the whole vector space. That's by definition of script S. Let's take an element V in B. I would like to prove it's in fact in C. And then we use again the sort of theorems that I reminded you of in the introduction. We have that V is in the linear span of C because linear span of C is everything. Yet C union the singleton V is still a subset of B, therefore it's still linearly independent. And therefore we can conclude from this that V is an element of C. So Since C is already assumed to be a subset of B, and now we've proven that everything in B is also in C, we have equality between B and C, and indeed that means that B is minimal. Any element of script S that is contained in B, B being a basis, must actually be equal to B. So as before, we have a nice corollary. A spanning subset of a vector space is a basis if and only if it is minimal among all the spanning subsets. That really answers, as I said, a question we had about linear span. The minimal spanning sets are bases. The proof is immediate. You apply our big theorem to L equals the empty set. That's of course linearly independent, and S being the whole vector space, which is obviously spanning. So now we are ready to answer a very important question. If you have a vector space, does it even have a single basis? It is not a trivial question. If we accept the axiom of choice, for instance, then the answer is always positive, and I will give you a supplemental lecture on that little topic for general culture, but it is beyond the scope of what I want to cover at the moment. But yes, under certain assumption, you can answer by the affirmative this question. But it is not true if you do not have the right kind of axiom. It doesn't have to be the axiom of choice, but you need some sort of assumption quite deep in your set theory to be able to conclude that an arbitrary vector space has a basis indeed. However, we do not need any complicated machinery to answer this question in a very special case, which is actually the main focus of our course, namely finite dimensional spaces. So now I am going to introduce a very important definition. A vector space is finite dimensional when it is a linear span of one of its finite subsets. The world of finite dimensional vector spaces is also the world of matrices, of dimension theory, and it is really where bases play a central role. What is essential about finite dimensional vector spaces is the following theorem. If E is a finite dimensional vector space, if L is a linearly independent subset of E, and if S is a spanning subset of E, with S finite and L a subset of S, then there exists a basis, B, of E, which contains the linearly independent set L and is entirely contained in the finite spanning subset S. So what I'm going to do here is prove this theorem using the characterization of bases as maximal linearly independent sets, but you could also reduce this proof using the characterization of bases as minimal spanning sets, and it may be a fun exercise to try. So just as in the theorem about maximal linearly independent sets, let a script L be the set of all linearly independent subset of E, containing this L, given by assumption, and contained in this S, also given by assumption. So first of all, as an observation, script L is not empty because it must contain in particular L. On the other hand, all the elements of script L are subset of the finite set S, and therefore they have cardinality as most the cardinality of S, which is some natural number because S is finite again. So if you look at the set of the cardinalities of all the elements in script L, it is a non-empty subset of the natural numbers with an upper bound. And so it has a maximum. Let's call that D. What does it mean to have a maximum? It means that there is some element in script L whose cardinality is D. There might be several, but there is at least one. But then, by definition of cardinality, this set B is maximal for inclusion in script L. If you have any set that contains B but is larger in L, it would have strictly larger cardinality, which would contradict the fact D is a maximum. And so, by our theorem, we know that this B is actually a basis of E, and it satisfies all the required assumption. It contains L and is contained in S as an element of script L. This is a very powerful theorem. An immediate corollary is that every finite dimensional vector space admits a basis. And the proof is immediate. Take your L to be the empty set that's linearly independent. And we know, and this is important here, we know that since we're talking about a finite dimensional vector space, there is a finite spanning set, call it S. So take that as your S in your theorem, and then the theorem tells you there is a basis between the empty set and your finite spanning set. Here you go. So every finite dimensional vector space in particular admits a basis. So now we can use a theory we have developed in this course to conclude that if V is a finite dimensional vector space, then V is linearly isomorphic to k to the n for some natural number n. And the way it works is once you find a basis, you go back to the first math slide after the introduction of this course, and you'll see that actually we have this isomorphism sigma, which is defined using this basis, but here the basis is finite. So the set of finitely supported function from your basis to the scalar is just really something of the form k to the n up to an obvious bijection. So this seems to be an interesting linear isomorphism, but be careful, it does depend on the choice of a basis to begin with. And second of all, we have now an interesting question, which is, can k to the n be linearly isomorphic to k to the m for n different from m? So this is, of course, starting the idea of the notion of dimension of a vector space. I want to conclude my lecture with a piece of terminology, because this is something we're going to have to deal with later on. So I define linear independence for sets, and so bases in this lecture are sets. However, sometimes it's also convenient to talk about families rather than sets. Okay? For instance, talking about the families of the columns of a matrix rather than the set. There is a difference here, is that in a set, an element can only appear once, if it appears at all, whereas in a family you can repeat an element again and again. And in fact, that's basically the only difference. So let me give you a few definitions. If you have a family, V sub j, whereas the index set is also going to be called capital J here, in a vector space V. So all these V sub j's are vectors in V, and there might be a lot. I have no idea about the cardinality of a capital J. But such a family is called linearly independent when, for any finite choice of indices, J1, etc., Jn, we have that if you take n scalars, T1, etc., Tn, and you have T1 V J1 plus T2 V sub J2 plus etc. plus Tn V sub Jn equals 0, then indeed again all the coefficient T1 and etc. Tn are all 0. So that's not a shocking definition, but I make a comment down there under my definition, which is, you have to be careful, there's a subtlety, but it's a very mild subtlety. It says that if you want to check that a family is linearly independent, it's the same thing as checking that the range of the family, which is a set, the set of all the vectors V sub j, is linearly independent, the set I've been discussing in this lecture, and that no two entries in your family are the same. Okay, that's the added piece. Is that, for instance, let's say we have one single vector that's non-zero in a vector space. So we know the singleton made of this vector is linearly independent. And the family that would consist of this vector alone is also linearly independent. But the ordered pair VV, which is a particular family, is not linearly independent because we repeat the vector V twice. And then it's easy to see what happens, right? Then minus V plus V is a linear combination with non-zero coefficients that's equal to 0. The reason why we don't have to worry about duplicates when we work with sets is because there are no duplicates in set. When you work with families, you have to worry about duplicates as well to claim linear independence. So this is the definition for linear independence for a family, and here down there is the little comment that it's exactly the same as checking at once that the range of the family is a linearly independent set and that there is no duplicate. So this is not very difficult. And then we say that a family is spanning when the vector space is spanned by the range of the family, so there's nothing new there actually. Duplicates don't matter for that. And a family is a basis when it is both spanning and linearly independent. So from there it's easy to see that the concept of basis for family is well defined, and all you have to worry about is make sure that a basis doesn't have duplicates. A basis is really just a way to index a basis in the sense of sets. You can index that as long as you make sure you don't create duplicates when you do so. So Now that we introduce finite dimensional vector spaces and we know they always have a basis, we're going to focus our attention on those. And the grand question is, how many vectors do you need to make a basis for a given vector space? And that's called the dimension. For that to be a meaningful definition, we need to check that actually the number of vectors you need to make a basis is always the same for a given vector space. So we'll prove this, then we'll prove some fundamental properties relating dimension and subspaces and dimension and linear maps.